Let's examine the considerations for wiring a 50 horsepower motor with a Wye-Delta starter for a hydraulic elevator pump, focusing on core compliance and best practices. The scenario involves a non-continuous duty 50 horsepower motor operating at 208 volts, 3-phase, utilizing a Wye-Delta starter to limit starting current to 3 times the full load amperage and to trip at 1 times the full load amperage during run mode. The system employs a Class 10 motor overload. We'll use THHN conductors installed in a combination of flexible metal conduit, electrical metallic tubing, and liquid type flexible non-metallic conduit with an ambient temperature of 40 degrees Celsius. The overcurrent protection device will be a standard inverse time breaker. The first step involves checking the line voltage range to ensure that the chosen starter and overcurrent protection device are suitable for the specified voltage range, which is 208 volts. Plus 15%, minus 10%. Next, you want to verify the motor overload settings and confirm that the starting current limit and the run mode trip settings are appropriate for the motor's characteristics. Per National Electrical Code Table 430.150, the motor's full load amperage is 143 amps. When sizing the motor conductors, firstly, according to section 110.14, C1, because the load is greater than 100 amps, it's reasonable to assume the use of terminals and devices rated for 75 degrees Celsius, allowing the wire ampacity to also be rated for 75 degrees Celsius. Secondly, according to table 310.16, the conductor ampacity must be derated to 0.88 for 75 degrees Celsius rated wire used at 40 degrees Celsius. Thirdly, per table 310.15, B2. The conductor ampacity must be further derated to 0.8 because the Wye-Delta starter requires 6 current-carrying conductors and 1 conduit to the motor, not 3. Fourthly, due to the use of a Wye-Delta starter, the individual conductor ampacity can be increased by 1 divided by 0.58, as per section 430.22. Fifthly, because of the non-continuous duty cycle motor in an intermittent elevator application per table 430.22. The ampacity can be further increased by 1 divided by 0.9. Therefore, the required motor conductor ampacity should be greater than 143 amps multiplied by 0.58 multiplied by 0.9 multiplied by 1.25 divided by 0.88 multiplied by 0.8, which equals approximately 133 amps. This requires the use of a total of 6 1/0 THHN copper conductors or larger, per table 310.16. It is important to confirm the conductor temperature rating. Ensure that the assumed 75 degrees Celsius rating for terminals and wires is correct based on the installation details. Review the derating factors applied to the conductor ampacity, considering the number of conductors in the conduit and the intermittent duty cycle of the motor. It's crucial to verify the intermediate steps and final result for the calculated ampacity of the motor conductors. To size the overcurrent protection device and equipment grounding conductor, firstly per table 430.52, an inverse time circuit breaker can be rated for a maximum of 2.5 times 143 amps, which equals 358 amps, and rounding to the next highest standard value per 240.6, this would be 400 amps. The minimum breaker size would be 1.15 times 143 amps, allowing the use of a 175 amp breaker. However, this might cause nuisance tripping, so sizing the breaker at the maximum allowable value is preferable. Secondly, per the opening paragraph of section 250.122, the equipment grounding conductor is not required to be larger than the motor conductors. Thirdly, according to table 250.122, for a 400 amp overcurrent protection device, 1/3 American wire gauge copper equipment grounding conductor or larger should be used. Verify the chosen equipment grounding conductor size based on the overcurrent protection device rating and National Electrical Code requirements. Confirm that the selected breaker rating of 400 amps is within the acceptable range based on the motor full load amperage and National Electrical Code requirements. For sizing the motor conductor conduit, Firstly, there are 6 1/0 and 1/3 American wire gauge THHN wires in the electrical metallic tubing. Therefore, the total area required by these conductors per Chapter 9 Table 5 is 6 multiplied by 0.1855 plus 1 multiplied by 0.973, which equals approximately 1.2103 square inches. Secondly, per Chapter 9 Table 1, the conductors can utilize no more than 40% of the electrical metallic tubing internal cross-sectional area. Therefore, the electrical metallic tubing must have an internal cross-sectional area of greater than 1.2103 divided by 0.4, which equals approximately 3.26 square inches. Thirdly, according to Chapter 9 Table 4, 2-inch electrical metallic tubing will meet this requirement at 3.356 square inches area, which is approximately 36% fill. Evaluate the conduit jam ratio. Confirm that the calculated conduit jam ratio is outside the problematic range to avoid conductor jamming issues. The conduit jam ratio is calculated as 3.356 divided by 0.486, which equals approximately 6.9. Since it's not within the range of 2.8 to 3.2, no conductor jamming issues are anticipated. In a real-life situation, beyond the considerations for an exam, there are several additional crucial steps. Firstly, it is important to review the equipment specifications. Verify that the selected starter, overcurrent protection device, and conductors meet the specific requirements for the motor and application. Secondly, consulting with manufacturers is advisable to obtain any necessary guidance or technical support from the manufacturers of the equipment and materials being used. Thirdly, assess potential hazards. Evaluate the installation environment and consider potential hazards that may affect the choice of materials or installation methods. Fourthly, secure necessary permits. Ensure that all necessary permits are obtained and that the installation is inspected by qualified personnel. And fifthly, documentation is important. Provide clear and detailed documentation of the installation, including calculations, component specifications, and any special considerations.